The last section of chapter 4 is, I guess, technically an application of derivatives, but not really. We're going to tie it back a little bit with our velocity and acceleration from back in, I think it was 4.6. But really, the antiderivative idea here is kind of our segue into chapter 5, where we're going to see how derivatives tie into the area that we talked about way back in chapter 1. So I guess without further ado, let's go ahead and start talking about what an antiderivative actually is. And I would imagine this is not a surprise because the prefix anti kind of sort of means opposite, but we are talking about the opposite of taking a derivative. Okay, so it's almost like an inverse function. We can't say inverse function because a derivative is not really a function, but just like, excuse me, division is the opposite of multiplication, or logarithms are the opposite of exponents. Antiderivatives are the opposite of derivatives. So, using a more hands-on example, if we took the derivative of, say, 5x cubed, just using our normal derivative rules, you're going to end up with a 15x squared. Right? Not a huge deal there. Just using this as an example to make sure it's clear that we can either say the derivative of 5x cubed is 15x squared, or we can turn this around, work backwards, and say that an antiderivative, we're turning it around, so antiderivative of 15x squared is 5x cubed. Okay, so that's just the idea of what's happening, is that we're not taking derivatives and getting a result. We're kind of taking the answer and working backwards. If I take the antiderivative of 15x squared, I should get 5x cubed. Okay. But there is a little bit of a hiccup here that we have to be aware of, and for now, it's just one of the annoying things to keep track of, but it plays a role in how we have to deal with things towards the end of the section. Notice I didn't say the antiderivative. When we talk about derivatives, there is just one derivative. The derivative of 5x cubed is absolutely 15x squared. Nothing else fits there. Okay, but when we're talking about antiderivatives, there are tons of antiderivatives of, excuse me, 15x squared. And let's just again do another example to show where this is kind of coming from instead of me trying to describe it. If I took the derivative of something almost identical here, so stick with the 5x cubed, but say instead of just 5x cubed, we had a 5x cubed plus 11. If I take the derivative, I'm still going to get 15x squared. Right? The derivative of a constant is just going to disappear. So if you wanted to write this in words, you would say that an antiderivative of 15x squared is 5x cubed plus 11. Okay, and that's why we have to use the word and. There's not just one. They're all going to have the same base. I guess I can't say polynomial. In this case, it's polynomial, but they're going to have the same base, I guess, function. But as long as I'm adding a constant here, when I take the derivative of the constant, it disappears, and you're still going to get 15x squared. So we can take the antiderivative, get 5x cubed plus 1, 5x cubed plus 32, 5x cubed minus 1/2. Right? So an antiderivative is technically what's called a family of functions, where they're all related by some base function, but they're different because up to a constant. So we could be adding or subtracting any sort of constant here that we want. Right? So it's going to seem a little bit like notation right now, but we absolutely need to keep track of that. And so the idea is that this 11 that I put in here can be any constant. So if I just replace this with some constant here, we're going to get that same constant back back at the end. And typically here, when we write our answer, this is the variation that we want to write. We want to write the 5x cubed plus c to make sure everybody recognizes, well, hey, it's not just 5x cubed. You can also have a constant added on to it. Right, so we're going to talk about a little bit of notation next, but that notation is going to tie in with the plus c that we just had. And so just like we have this kind of dx notation for derivatives of things where we're not naming a function, we have a similar notation that involves dx with our antiderivatives. I guess as I'm erasing, I'll kind of talk through this to make sure it's clear. Now remember, the d's kind of tell us we're taking the derivative. The x tells us what we're taking the derivative with respect to. So that's one of the benefits of that notation, is that you don't have to guess, with that prime notation. You have to just be aware of what you're taking derivatives with respect to. But here, it's telling us flat out. With antiderivatives, we don't really have that too much of a shortcut notation here. But there's two different notations that we have to be aware of. Okay, so the first one is kind of the notation where you're just assuming that you're taking the antiderivative with respect to the variable at hand, and we don't actually write it out. But an antiderivative of the original function f of x is, by notation, capital F of x. Okay, so this is certainly not universal outside of a calculus class, but within a calculus class, anytime you have a function named using a capital letter, it's named that way because it's the antiderivative of the associated lowercase letter function. Okay, so just like the derivative of f of x would be f prime of x, the antiderivative of f of x is capital F of x. And again, this notation's a little bit wishy-washy because you have to be able to recognize that we are dealing with the x as part of the function notation and hope that that's what we're taking the antiderivative with respect to. Remember, that's not always the case. When we were doing some of our applications, excuse me, especially at the end of chapter 3, we were taking derivatives with respect to t, even though there were no t's in the initial problem. Sometimes that same thing could happen in outside classes. So you're not necessarily always taking the antiderivative with respect to x. So this just relies on the common knowledge within the problem. If everybody says, well, hey, we're taking the antiderivative with respect to x, you don't have to write it out. You can use this notation. If you wanted to write out, excuse me, better notation to make sure it's clear that we're taking the antiderivative with respect to x, the notation is actually the same integral sign that we had when we were talking about net area. We don't put endpoints here because we're not actually finding net area between x values. This is just the same notation, but the antiderivative of a function f of x with respect to x is equal to that same antiderivative notation. So just to be clear, that this is still antiderivative notation here. There's just two parts of it. This tells you that you're taking the antiderivative. This says that it's with respect to x. Okay, so don't let this mess you up. Sometimes it feels like that's part of the expression that you might be working with and have to deal with. But this is here nothing more than to label what you're taking the antiderivative with respect to. Okay, so, you know, in words, this is the antiderivative of f with respect to x. And so this is kind of how the two notations play together. We just got done saying that you can use the capital F notation for antiderivative, or you can use this notation. This is going to be a lot more common in this section at least, but going forward, we're going to kind of use both of these depending on the context of the problem. And not to go all Dora Explorer on you, but what's missing? And so from the previous discussion, we said that there's not just one antiderivative. And so up here, we usually don't bother writing the plus c because we're kind of assuming that that plus c is incorporated within this function already. But if you have this notation, we almost always write in at the end here a plus c because of the way we end up calculating and thinking through the problem with this notation. So we typically do write the plus c here to make sure it's clear that you can add or subtract any constant you want and still get a correct answer. So I guess the moral of the story is as we do this, we're going to focus on the, quote, easy antiderivative, figure out what the easy antiderivative is, write that down, and then just make sure to put a plus c at the end to incorporate everything else. All right, so we have a little bit more to talk about before we can actually start taking antiderivatives, but that's the definition and the notation. All right, so before we get into specific antiderivatives, we need to talk about the basic properties of general antiderivatives. So just like when we were finding derivatives, it was pretty important that we knew that the derivative of a constant times a function is just a constant times the derivative, so on and so forth. So we're going to go through those rules here as well. Right? So I guess maybe I should have been writing this as I talked about it, but that is kind of our first example. If we're looking for rules for antiderivatives, they're all going to be based on the derivative rules that we already know. So if I take the derivative of a constant times some function, our constant multiplication rule just tells us, well, hey, that constant stays. Right? So, excuse me, we end up with a times just the derivative of f of x is f prime of x. And so that's our constant multiplication rule for derivatives. And so we're just going to do two things here to create a rule for antiderivatives. One is to recognize that this rule works for any function in the world. So typically we're just working with a generic function, but if we happen to know that we're working with an antiderivative, we might as well use the antiderivative notation. And then we can just plug it in over here and say, well, it's still the constant times the derivative of the antiderivative. Okay, but what's the derivative of the antiderivative? I guess I didn't bother to write this down previously, but by definition, antiderivatives and derivatives are opposites. So this is nothing more than the constant times the original function f, not the antiderivative f. Okay, so maybe I'll write this off to the side just to make sure it's absolutely clear. But if you take the derivative of the antiderivative, you're absolutely going to get the original function. Or if you wanted to use the other notation, if I take the derivative of the antiderivative, you're going to get the original function. Okay, so neither one of those should be a surprise. I just didn't think to write it out in the previous screen, but this is just nothing more than just the definition. Okay, so we're using this first one. The derivative of the antiderivative is the original function itself. So right now you're probably thinking, well, this is still not an antiderivative rule. You've got that derivative symbol right here. And so the final step, other than kind of flipping things around, is to just say, well, this is an equation that we can use equation rules that basically say, as long as I do the same thing to both sides of the equation, I don't change the truthiness. So if the derivative of a times f of x is equal to a times regular f of x, then the antiderivatives have to be the same. Okay, so we're going to start with this one, just so that the rule looks a little bit easier, because this is the last line that I'm going to write. So here, there's nothing to simplify, right? We want this to be an antiderivative rule, so we need there to be an antiderivative somewhere in our rule. So the antiderivative of a times the function f of x, remember again, a is a constant. So all we're doing is flip-flopping. Over here, now we just kind of wrote this out, the derivative and the antiderivative cancel out. Okay, so just be careful again, just a warning, I've said this before, but the antiderivative has two parts to the notation. So it's not that just these two cancel out, there's still a dx hanging out there. That dx is part of the notation, and that's kind of why we use d over dx. There's a lot of different reasons, but you can kind of think about this as division. It's not really what's happening, but you can think about the dx is canceling, and then the antiderivative and the derivative canceling. But regardless, they all cancel out, and we're left with, excuse me, the constant times the antiderivative of x. And once again here, because we took the antiderivative of both sides, we didn't actually figure this one, but this one we kind of did. There does need to be a plus c over here. Okay. So, excuse me. So again, you don't really have to have that plus c. That's not something our textbook concentrates on, but if you took the derivative of both sides here, the derivative constant would disappear and things would end up, matching up. So let's just kind of get rid of it because I know the textbook doesn't write it, but that plus c is still a role if you're looking at an actual calculation that we are doing. Okay, so this is something where our textbook doesn't give these names, so I'm not going to bother to write it out, but this is nothing more than the constant multiplication rule for antiderivatives. The antiderivative of a constant times a function is equal to the antiderivative is equal to the constant times the antiderivative. And so that's obviously a hugely important thing to be able to recognize, because otherwise, if you knew how to take the antiderivative of x squared, if you didn't know this rule, you would have no idea how to take the antiderivative of 2x squared. And so this is something that we should bear in mind, that we have the nice, same basic idea with constant multiplication that we had when we were working with derivatives. And so I'll try to speed the next one up. But the next one is nothing more than the sum rule. So this go around, we'll just write out the sum rule again. But this time, let's just go ahead and start with the antiderivatives. If I take the derivative of the antiderivative of f plus the antiderivative of g, then, excuse me, Our derivative rule says that we just take the derivative of each of these individually, right? We can just work term by term with derivatives. So this is nothing more than the derivative of the antiderivative, remember, would be the original function. The derivative of the antiderivative is, again, the original function. Okay. And then once again, all this is take the antiderivative of both sides with respect to x. Here, we're going to leave the antiderivative so that we actually have a rule that we can write out nicely. So the antiderivative of f of x plus g of x with respect to x is equal to, up here, the derivative and the antiderivative cancel out. It's equal to the antiderivative of f plus the antiderivative of g. And again, technically there's a plus c over there that's we don't worry about because we're not actually calculating, but if we had actual functions over there, we'd have to make sure there was a plus c at the end. Okay. So this is your sum rule for antiderivatives. The antiderivative of the sum of two functions is just the two antiderivatives added together, along with the constant if you're actually dealing with the calculation. Right, so those are the two main antiderivative rules that we're going to work with now. I'm going to show you why we don't work with the product rule and the quotient rule. I'm not even going to talk about the chain rule right now because that's actually something we'll handle in chapter 5. But I at least want to make sure that it's clear that if we keep going through the same sort of process to try to create new antiderivative rules, that it doesn't quite break down, but it just becomes almost useless. Okay, so if I'm looking at the product rule says that if we take the derivative of the product of two antiderivatives, this one I'll write out a little bit more formally just because it's a little bit hard to keep track of, but the product rule says take the derivative of your first function, multiply it times the second function, then add on the derivative of the second function, multiply it times the first function. And as we said before, the derivative of an antiderivative kind of just cancels out and gives you the original function. So I have the original function original function f of x times the antiderivative of x plus, this would just give you the original function g of x times the antiderivative of f of x. Okay. And hopefully you can kind of already see if we did the exact same thing we usually done, where we just kind of recopy this over here, evaluate and the antiderivative on the other side, it's just going to be too messy. Okay? We'll just go ahead and write it in and do it and talk through it. But the moral of the story is that you would end up with the antiderivative of a really weird combination of functions, a very specific combination of functions that would allow you to figure out what the product was. So over here again, the antiderivatives and the derivatives cancel out. So this is not an incorrect rule. This is absolutely correct. But just think about how hard it would be to recognize an expression that looks like this. You'd have to recognize two separate functions where their antiderivatives appeared in the other portion. And keep in mind, these things might be actually multiplied together and foiled and all of that sort of stuff. This is really, really, really difficult to recognize. So I don't want to say this is universally too tricky, because you learn some tricks in calculus 2 to allow you to kind of deal with this. But for this class, this is just too hard to recognize to be useful right now. Okay, so again, I don't want to completely, just dismiss this, because if you are going to calculus 2, this is a different variation of something that you learn to do in that class. But in this class, it's just too much to try to figure out a way of recognizing that pattern and make it something that we can use. Okay, so that's why we don't bother writing out, like a product rule for antiderivatives. It's just too tricky to work with. I'm not going to write out the quotient rule, because if the product rule is too hard, the quotient rule is going to be just as hard. You have the same basic pattern in the numerator. You'd just be subtracting instead of adding, and then you'd have the extra denominator. I said earlier that I wasn't going to mess around with the chain rule, so I'm not going to say much, but I am going to kind of write it out just so that it's not completely new when we talk about it in chapter 5. But if you're looking at the chain rule, I'm going to just kind of take a little bit of, I guess, creative license here to say at the beginning, if you're working with the chain rule, it's really impossible. So don't write this down because I'm about to change it. It's impossible to be dealing with two antiderivatives at the same time and make much sense out of it. Okay, so in the past, this is how we've been working with it. We've been taking the derivative of two things that were both antiderivatives to begin with. I'm going to tell you immediately when we use this in chapter 5, we're not going to try to work with two antiderivatives here. We're going to work with one antiderivative that happens to be the outer function, and the inner function we're just going to let be a regular function. Okay, but then after that, it's the same progression as always. We actually use the rule. So our chain rule says take the derivative of the outer function, evaluated at the inner function, and then multiply times the derivative of that inner function, which is, if I take the derivative of that antiderivative, I get the regular function of f, evaluated g of x, times the derivative of g of x. Okay, so comparing to what we just talked about with the product rule, one of the hard things about the product rule was that we were mixing and matching between the regular functions and the antiderivatives. At least here, they're all regular functions. And that's how this is going to become useful later on. So again, I'll just go ahead and write out the rule. Sorry, I forgot to write the dx before I actually did it. I'll just rewrite the relationship that we'll use in chapter 5 so that you're exposed to it just a little bit here. So the derivative and the antiderivative cancel out. We'd end up with the antiderivative of a function evaluated at g of x times the derivative of g of x is equal to the antiderivative of the outer function evaluated at the inner function. Okay, so I'm going to try not to talk any further than this. Maybe I should have boxed it, but this is a pattern that's not as bad defined. Inner functions are usually easier to find because they're inside of a parenthesis or inside of an exponent or inside of a fraction. This is a little bit easier to pick out. And because we are really comfortable with taking derivatives, it's not really a problem that there's a derivative in our function. Once we figure out what the inner function is, we just check, hey, is there a derivative of that inner function somewhere within my expression to be able to handle that g prime of x? And if we can make that work out, then sure, we can find the antiderivative. It's still a little bit complicated, which is why we don't actually do this until chapter 5. But just be aware, this is coming up. We are going to be reversing the chain rule. Right? So I guess quick overview with what we just finished up in this context. We absolutely want to be able to use the constant multiplication rule for antiderivatives and the sum rule for antiderivatives. But there is no real product rule or quotient rule for antiderivatives that we ever use in this class. And the chain rule, we're just going to have to wait until chapter 5, and we have a little bit more experience under our belt to work through with that one. All right, so, excuse me. So now let's talk about some antiderivative rules for individual functions. Okay, so we're going to kind of set this up in the same way. So one of the first things we talked about was the derivative of a constant. So I'm going to use a for my constant here so we don't get it confused with the plus c that we've been talking about. But the derivative of a constant is just 0. Okay. So this is kind of a silly thing to say, but I wanted to bring this up because if we just take the antiderivative of both sides, what we get then is the antiderivative of 0. So I'm just flipping it around like always. The antiderivative of 0 with respect to x is equal to some constant. Okay, so that's just another reason why you can look at something and say, well, I always have a plus the constant at the end because I'm kind of taking this off to the side a second. That then, of course, means that if I have f of x dx, that's the same thing as f of x plus 0. So this is not something you would ever do. I'm just trying to tie in and give you other reasons to keep in mind of that constant. And then we don't know the antiderivative other than to say that it's capital F. And I guess technically I am using my sum rule here. I'm taking the antiderivative of f plus the antiderivative of 0. Here I was using a as my constant just to keep it separate again, but the constant in our answer is usually a c. Okay. So again, I was just trying to give you something silly to start with, just to give you one other reason or one other idea and how we can verify or understand that there does need to be a plus c at the end of the rest of these. All right, so this one I don't want you to actually worry about because it's not really something that comes up because we're automatically putting the plus c into the relationship on our own. The first real derivative rule that makes a difference for us is just the derivative of a times x. And again, if there's just an x with no exponent or anything else happening to it, the derivative is just the coefficient on the x. Okay, so this one, kind of makes sense to have a rule for. If I take the antiderivative of a, okay, so the antiderivative of a should give me a times x. Okay. But again, you always have to have that plus c at the end in order to be 100% correct. Right? So that's our first, I guess, actual calculation, is the antiderivative of a constant is going to give you an expression that would give you a line. We would have the coefficient on x and then add on some random constant that we would have to either figure out later on or just leave as a placeholder. Okay, so that's the easiest of our rules. From there, we kind of build up to our power rule. Okay, so what we have right now is the antiderivative rule for a constant gives you an ax plus c. If I use the power rule, so that we can handle the antiderivative of any x raised to an exponent, we have to maybe write this out in words to make a little bit more sense out of this. But the derivative of x to the n is going to be n times x to the n minus 1. Okay, so I guess the point here is if you really wanted to, you could take the antiderivative of both sides like we've just been doing and say the antiderivative of n times x to the n minus 1 is equal to x to the n. That's a really hard formula to use. So instead of doing that, let's just write out, descriptively what's happening here. When we do this, we never really use the formula. At least I hope you guys aren't using the formula. But you just multiply by the exponent. And once you're done multiplying by the exponent, you're decreasing the exponent by 1. Okay, so if we're talking about doing an antiderivative, instead of worrying about reversing the formula here, let's just reverse the process of what we have. Okay, so if I'm taking the antiderivative of x raised to a power, then if I'm going to reverse the process, I have to go in the opposite order and do the opposite kind of operation here. So I'll fill in this blank here in a second, but the first thing that we would do is instead of decreasing the exponent by 1, we would have to increase the exponent by 1. Oops. Okay, so what we'd end up with is an x to the n plus 1 over here. And then the second thing we would do is instead of multiply by the exponent, we would divide by the exponent. And you can use division if you want, but in the way that these are going to be written out, it's almost always easiest to remember that dividing is really multiplying by the reciprocal, especially if you end up with fractions that are already in your problem. So I'm just going to go ahead and write it out that way. So the opposite of multiplying by the exponent is multiplying by the reciprocal of that new exponent. And I'm just writing new here because I just want to make absolutely certain that the order is important here, right? So up here, we multiplied by the exponent first and then changed it. Here, we have to change it first and then multiply by its reciprocal. So we're going to multiply that by 1 over n plus 1. Okay. And that is the rule that we're really wanting to try to memorize. It's a little bit easier to keep track of than this sort of idea in working backwards, because obviously this matches up. It gives you a direct relationship with the antiderivative of an actual term instead of this weird relationship. Okay, so this would be your power rule for antiderivatives. All right, so we'll take a pause before learning other specific rules here, but between the sum rule, the constant multiplication rule that we learned just a few minutes ago, along with this power rule and the antiderivative of a constant, we're ready to be able to take the antiderivative of a polynomial. Okay, so let's just do an example. I don't think we'll need to do more than one because there's nothing here other than using the rules that we just talked about. So let's say that you're asked to find the antiderivative of maybe 3x cubed minus 2/5 x squared plus 7/2 x minus 1, just to make sure that we have plenty of practice here. And so I'm going to be a tad bit annoying here and break this down. This is something you would normally mentally do, but there's kind of two things that we should be aware of. One is that because of our sum rule, we are taking the antiderivative term by term. And also because of our constant multiplication rule, we can kind of ignore the coefficients, just make sure that they're multiplied at the end. So what we're saying here is this is the same thing as 3 times the antiderivative of x cubed with respect to x minus 2/5 times the antiderivative of x squared with respect to x plus 7/2 times the antiderivative of x dx minus the antiderivative of 1 dx. Okay, so it's again, we're working with 1, 2, 3, 4 different terms. And with each of these terms, we just pull the coefficient out in front. Okay, so with a little bit of practice, you don't necessarily have to write this out or write the coefficients separately, but this is the easiest way to get yourself used to the process. Okay, so now we're looking at 3 times the antiderivative of x cubed. So our rule for that was to increase the exponent by 1 and then multiply by the reciprocal of what you just wrote. Okay. Now, I don't want to talk about this in too much detail now, but technically remember, the antiderivative is going to give you a plus c for a constant here. But we're also going to get a plus c here, a plus c here, a plus c here. And so we don't really worry about it until the end because that c just represents a generic constant. Even if I wrote, 4 different constants here and then, multiplied by the 3 and multiplied by the 2/5, when we add all those up and multiply and all that, we're just going to get another constant. And we can just name that constant c instead of that weird combination of individual constants. So in the middle of a problem, you don't worry about the plus c. You just say, well, hey, that's the basic antiderivative for x cubed. And the next one, same idea. The basic antiderivative for x squared is you increase the exponent by 1, multiply times the reciprocal. The basic, excuse me, antiderivative of x is to, again, raise the exponent by 1, multiply by the reciprocal. Sorry, I got going too fast here. We're done with the antiderivative. So that was correct, but it's not the antiderivative anymore. We took the antiderivative to get the 1/2 x squared. And then finally, the antiderivative of 1 is just x. Okay, right. So all of these, the first 3 was raise the exponent by 1 and then multiply by the reciprocal. The last one uses the antiderivative constant. You just end up with the variable attached to whatever number you started with. And if you want, you can always check your answer before you go forward. If I take the derivative of 1/4 x to the 4th, I multiply by 4, that cancels out. Decrease the exponent by 1, I'm going to get 3x cubed just like I started. So you don't have to, but if you're ever concerned about whether you've done it right or not, just take the derivative and check. And now it's just a matter of doing some multiplication. 3 times 1/4 is 3/4 times x to the 4th power. Here, multiply straight across to get a 2/15 x to the 3rd power. Multiply straight across again to get a 7/4 times x squared. There's nothing to do here other than subtract the x. And then finally, this is where you want to put your plus c at the end. Every antiderivative in the world of that polynomial is going to have this basis, but it can have different constants added at the end. You can have a plus 1, you can have no constant, you can have a minus 3/8, whatever it happens to be. So this is your first example of actually calculating an antiderivative based on a polynomial, right? And once again, not that you have to do this, but if you really want to go through and triple check, if you take the derivative of this expression, you better be getting the original polynomial that we started with. Right? So moving on, there's one thing that we have to be very careful about with our power rule. And I guess I should lead up to it a little bit instead of just sticking right with it. But just make sure that it's clear first that the power rule can be used to do something that's not clearly just the power. You know, we can take the antiderivative of, say, 2 over x to the 4th using the power rule. Okay, so here it looks like a quotient and all that. And I know some of you have been doing this naturally anyway, but if you haven't been, now you need to start. This looks like a quotient, but we can always rewrite a fraction that has a single term in the denominator just using a negative exponent. And we can move this up by changing the sign in the exponent. Okay. So from algebra, I heard some students say this a couple of years ago. If you cross the line, you change the sign, and that's it. Okay, so we've gone from something that kind of looks like a scary fraction to something that is annoying because we have a negative exponent. But other than that, we have a rule for this. Okay, so our rule is, once again, keep the coefficient, then raise the exponent by 1. So if I add 1 to -4, I'm going to get -3. Multiply by the reciprocal of -3, which would be -1/3. Okay. And since there is just one term here, I am going to need to put a plus c. And beyond that, you're just multiplying 2 times -1/3 is -2/3. So you have -2/3 x to the -3rd power plus c. And it's completely up to you whether you want to leave it as a negative exponent or rewrite it as kind of a fraction format. I would tend to tell you to leave it as a negative exponent because it's not worth the extra time. Okay, so that's just showing that you can use the power rule in some situations with negative exponents where maybe you have to do a little bit of converting. And so, like I said, I was trying to leave this in just a little bit, but what if I asked you to take the antiderivative of 1 over x? Okay. So, excuse me. If I ask you to take the antiderivative of 1 over x and you try to use the same property here, this would be the same thing as x to the -1st. Right? The exponent, there's a 1 that's not really there. If you move it up, you have to change its sign. You can leave the 1 out in front if you want to, but there's no need to. And then if you try to use the power rule here, what happens? You add the 1 to the exponent, you get x to the 0th. And then you have to multiply by the reciprocal of 0. And that should be a huge red flag. You definitely cannot divide by 0. And so this would be undefined, which is not the actual answer here. You can actually take the antiderivative of 1 over x, but you cannot use the power rule. Okay, so the moral of the story is I didn't want to bring this all at once because it would have gotten just a little bit messy, but you cannot use the power rule with an exponent of -1. You can use it with anything else. Now, it would be kind of silly to use it with an exponent of 0, but it would still work. Okay? But you know, whether it's -2/3, +3/8, +10, -20, all of those things work, but you cannot use the power rule with an exponent of -1. So this kind of segues into our first kind of specialized rule. I just said that we have to be able to find the antiderivative of 1 over x because that's a pretty common expression to run into. So you know, just kind of think back to how you work with inverse functions, especially in trigonometry. You know, if you're trying to find the antiderivative of 1 over x, you're trying to ask yourself, well, what would I take the derivative of to get 1 over x? Okay. And hopefully this says something you remember towards the end of chapter 3. The derivative of natural log gives you 1 over x. And if I take the derivative of natural log, you get 1 over x. So turning this around, this means that the antiderivative of 1 over x dx is equal to the natural log of x. Okay. So there's a little bit of a technicality that we need to talk about here. because it's actually a little bit more expansive than this. But two things. One, the obvious thing, we still have to have the plus c. But to make this rule as general and as usable as possible, we're actually also going to be able to put an absolute value around the x. And that's something that's really very important to get used to. So if you just remember the properties of logarithms, we can't take the logarithm of a negative number, okay? So if we were working with, like 1 over negative, x plus 3 or whatnot in a more advanced problem, we'd be in a little bit of trouble, trying to deal with that negative sign, depending on the context of what's happening. So if we have an absolute value here, we still can't take the natural log of 0, but now at least we can take the natural log of any positive number. So that doesn't matter whether you plug in a positive or negative in here. It really just kind of expands what you're allowed to put in there. So we do need to talk about why this works here. I know this is usually what we have memorized because this is usually what we ran into. But in order to show this works, all we have to do is figure out what is the derivative of the natural log of absolute value of x. Okay. And keep in mind, it's been a while, but when we talk about, absolute value, we automatically rewrote that as a piecewise function. Okay. So we wrote that as just a regular x if x is already positive, and it would be negative x if x is negative. And notice here, we don't have the equal to on either one of those because we can't take the natural log of 0. But that's just our definition of what the absolute value is. We don't do anything to the value if the value is already positive. If the value is negative, we do the opposite so that it becomes positive. And then from there, we only had maybe one example of this, but if you take the derivative of a piecewise function, it's nothing more than taking the derivative of each individual piece. And so in the numerator, not the numerator, but in the first one, it's just your standard derivative. The derivative of natural log is 1 over x if x is greater than 0. Here we have to use the chain rule. Okay, so the derivative of the natural log is going to give you 1 over whatever you're taking the natural log of, and then you have to multiply it times the derivative of the inner function. Well, the derivative of the inner function is nothing more than -1. And you can see immediately what happens. The 1 over negative x and the -1 is going to multiply to just 1 over x. Okay, so what that's really telling us then is kind of coming back to the top. It doesn't matter whether x is larger than 0 or smaller than 0. The derivative is 1 over x either way. So the derivative of natural log of the absolute value of x is equal to 1 over x. If you wanted to be a little bit more picky here, you would have to say as long as x is not equal to 0. But hopefully that's clear because you can't take the natural log of 0. You can't divide 1 by 0. So that's something that I don't know that you'd necessarily need to write. Okay, so again, I don't want to overdwell on the absolute value portion of it, but it is something we want you to get used to because this actually expands the applications that you can use derivatives and antiderivatives for in upcoming applications. Right. So this is, I guess you would call this the antiderivative rule for a logarithm. You're not taking the antiderivative logarithm, but this is the antiderivative that gets you a logarithm. Okay. And so excuse me, that's our very first specialized rule. And the power rule was something we can apply to a lot of different functions. Same thing with the constant multiplication rule, the sum rule. This one is very specific. You have to be working with either 1 over x or x to the negative first power, and it drops in a natural log. Right? So the only other types of antiderivatives that we're left with discussing is working with exponentials and trig functions. Right? So in both of these, we're going to kind of use a guess and check sort of idea. Okay? So basically, starting with exponentials, we can look through this and remind ourselves immediately that the derivative of e to the x is e to the x, which of course, turning this around means that the antiderivative of e to the x is equal to e to the x. Okay, but I'm sure that you've noticed that there's plenty of examples that we've done out there, especially if you remember some of your formulas from algebra involving like compound interest and stuff like that. We pretty often have things other than just an x up here. So if we were dealing with, I guess I'll use an actual example here. If we were dealing with e to say 0.05, let's actually switch a couple things up here. We've been using x's all over the place. I just want to make sure it's clear. You don't have to be working with x's. You can be working with any variable you want. And so just as a quick reminder, you very often end up with logarithmic or exponential growths having some sort of coefficient in front of your time component. So let's just say we're trying to find the antiderivative of this. Okay. So because we know the antiderivative of e raised to a power is e itself, our first guess might just be that it's e to the 0.05t plus c. And I should have written that up here as well. I apologize, I forgot about it there. So that's our guess, that it follows that same sort of pattern. Okay, but check this. If that's our antiderivative, we should be able to take the derivative and come back to our original function. If you take the derivative of e to the 0.05, I messed up because I forgot that I was switching to a t. But if I take the derivative with respect to t of this, then we do get e to the 0.05t as our first step, but this is a chain rule problem. We're not just going to get the e straight back. We have to multiply by the derivative of the exponent. So the derivative of 0.05t is 0.05. Okay, so putting that all together, we end up with 0.05 times e to the 0.05t. Okay, so our guess is wrong by that constant. It's constant multiplication, so this is actually a pretty easy fix, right? So when we took the derivative, we were at 0.05 too much. We would need to cancel this out in order for this to be correct. So if there's a 0.05 out in front that we don't want there, our next guess would just say, well, we've got to make sure that that cancels out. To cancel out multiplication by 0.05, we would have to multiply by the reciprocal or divide by 0.05. Okay. And hopefully this makes sense that it'll end up working pretty nicely now. And so I'm not going to erase everything. I probably shouldn't have erased what I just wrote down there. But if we take the derivative with respect to t of 1 over 0.05 times e to the 0.05t, then I didn't quite hit that right. Then the derivative of this, you would start by just saying, well, that constant coefficient is going to stay for a second. Derivative of e stays itself. Actually, let me just write that out. The constant coefficient stays. The e stays. But then you have to multiply by the derivative of the exponent. So you end up multiplying by that 0.05. And these guys just cancel out. And that is exactly what we started with. So we're in great shape here. So that's no longer a guess. We checked it, it worked out, and so we're good. And so worst case scenario, you can kind of use that idea to deal with variations of e to the x. Just realize that the antiderivative of the regular e to the x is itself. If there's something more going on, you can kind of guess and check your way into the correct answer. That said, I think there's a pretty obvious pattern here. Basically, all we're doing is, again, keeping the exponent exactly the same, because that's what we always do when we're working with derivatives and exponents, or exponential functions at least. But whatever the coefficient on the variable is, we need to take the reciprocal of out in front. Okay, so to write this out generically, and I'll recopy this in a second, but if this was just some random constant, I won't write the whole thing, or rewrite the whole thing, but if this was some random constant, say a times t, then it would stay as an a times t. We'd have to multiply by the reciprocal of a. And so that worked out a little bit more nicely than I thought, so I'm not going to recopy it. So, so generically here, we have kind of two rules for our exponential e. I'm not going to worry about taking the antiderivative of something like 10 to the x or 3 to the x. We talked about those derivatives, a little bit previously. It's just not something that is going to come up and that we need to deal with. But if we happen to have a straight out e to the x, it stays the same. If there's a constant multiplication in your exponent, then everything stays, but you have to be multiplied by the reciprocal of that constant. As a heads up, if we had anything other than constant multiplication here, if it was more complicated like a t squared plus 4, then we would end up having to use that chain rule formula that I talked about before, but that's later on again in chapter 5. So we're not going to do anything more complicated than maybe having a number times the variable up in that exponent. Okay, so we still have to talk about our sine, cosine, things like that. But let's just do an example, putting some things together with what we've talked about so far. So let's say we're looking at the antiderivative of x to the negative 3/4 plus e to the negative 7x minus 1 over 3x. And again, that dx is just part of our notation. All right, so here, there are actually the 3 main rules that we talked about. That is just going to be the power rule because we have the variable in the base raised to a constant exponent. This is going to be the exponential rule we just talked about since our variable's up in the exponent along with the e that gives it away. And this, if we rewrote it, would have a -1 as the exponent, which is not the power rule. That's the only time we can't use the power rule. This is the one that's going to give us a logarithm. And so just 3 different steps here. The first one, you end up adding 1 to the exponent. So just be careful with your calculator and or get common denominators, that sort of thing. But -3/4 plus 1 is 1/4. And then we have to multiply by the reciprocal of 1/4. Well, the reciprocal of 1/4 is just 4. So that's a little bit easier than some of the other ideas that we had, but that's our first step. And again, if you want to double check it, just go through and take the derivative. The derivative you multiply by the exponent, 1/4 times 4 would cancel out. Decrease by the exponent by 1 gives you the -3/4. So we're good there. Then moving on, we have that the antiderivative of e raised to an exponent is e raised to that exponent, but we also have to multiply by the reciprocal of the coefficient. So the reciprocal of the coefficient would be 1 over -7, and maybe making that look a little bit more nice, adding a negative is really just subtracting. So the next term we get 1/7 e to the -7x. And again, this would be a little bit harder to check, but if you took the derivative here, the exponential is the exponential itself. You'd have to multiply by the derivative of the exponent, which will give you -7. The -7, the -1/7 would cancel out to a +1 or just a plus e to the -7x. Okay, so maybe I should have labeled these. I said it, but this is the power rule. We haven't really been giving these names, but if you wanted to call this a name, this would be your exponential rule. And the last one I've already mentioned is going to end up being our logarithm rule. But let's say you didn't just notice that immediately, right? So if you didn't notice that, maybe you tried to use the power rule with that 1 over 3x. And in order to do that, you would have to move the x to the other side to get a normal looking problem, but that would give you a 1/3 x to the -1st power. Okay, and so just rewriting this and trying to use a power rule at this point, hopefully, is where you recognize, oh, wait a second, that's the one that doesn't work. But if you just took this a step forward, you would look at this and say that if I took the antiderivative, you would have to increase the exponent by 1 and multiply by the reciprocal. And all I'm showing here is if you have a hard time remembering when to use a power rule and when to not, if you just do it, if you just try it doesn't take more than 20 seconds to try this. As soon as you see that, you'd have to stop and say, wait a second, that's not the power rule. I remember looking at that in the textbook or watching the video and Mr. Farmer saying, be careful. That's not the power rule because you can't divide by 0. So I'm just kind of showing what goes wrong if you accidentally use the power rule. That's what kind of tells you that you have to remember that this is what I would call the log rule, even though it doesn't have a name. Okay, so what we have here, just to be a little bit safe, at 1 over 3x is kind of the same thing we did here. We can split this out. This is 1/3 times 1 over x. So that 1/3 would be the constant coefficient that stays. And then the antiderivative of 1 over x is the natural log of the absolute value of x. Okay. And we're basically finished. I don't know that there's too much to rewrite, but I got a little bit close here, so I can't quite put in that plus c. But at the end of the day, if you take the derivative of the natural log, you get 1 over x, and so 1/3 times 1 over x gives you the 1 over 3x, you know you're good. So our final answer is 4x to the 1/4 minus 1/7 e to the negative 7x minus 1/3 times the natural log of the absolute value of x. And I should just say this very carefully, it is always around the x in the natural log, not the whole thing. That is a huge difference. And then finally, we do have that plus c still. So that puts what I would say are kind of the 3 main rules that you run into most often as you're calculating. It puts those 3 rules into the same problem. Okay. So again, just realize that the log rule and the power rule are very similar. If you make a mistake, it's not a huge deal as long as you remember what to do when you run into dividing by 0. All right, so one last basic idea to talk about, and then we'll do a little bit of application work where we add on a little bit of extra information and be able to put it all together. So, excuse me. I forgot what I was doing for a second. We're working with our trig functions. So this is really going to mimic exactly what we did with our exponential functions. I'm not going to do this with every single trig function. We'll just write out the rules after we deal with sine. But we know that the derivative of sine is cosine. Okay, so turning that around, we know that the antiderivative of cosine of x is sine of x plus some constant. Okay. So that's our kind of first major idea here. But as we did before, we have to be careful that we're able to do variations. It's not always going to show up as the antiderivative cosine of x. Maybe we're looking at the antiderivative of cosine of 3x. And you can probably already guess what's about to happen here, but I'm going to play the long game here again and just say, well, if you don't remember the rule, just guess. You know, if we remember this part of the rule, we would at least be able to guess, well, hey, the antiderivative of cosine should give me sine. I'm taking cosine of 3x, so I should be taking sine of 3x, and I have the plus c at the end. Okay. But of course, if you check this, if you take the derivative of sine of 3x, you're going to get cosine of 3x. But again, it's the chain rule. The outer function is cosine, evaluated at the original function, and then we have to multiply that times the derivative of the inner function. Okay. So this does not match the original function we started with. It has an extra times 3 here. Okay. So guess what we have to do? We have to cancel that times 3 out. The opposite multiplied by 3 is multiplied by the reciprocal of 3, so we get a 1/3. And again, that's not really a guess anymore. If you really want to double check it, you can, but if you throw the 1/3 in front of all this, I'm going to try to just squeeze it in because I know this is getting a little bit of a long video. If I squeeze that 1/3 in, you'd have a 1/3 out in front. The 1/3 and the 3 cancel out. You are right back to what you started with. Okay, so the exponential rules and the trig rules all have the same kind of pattern in that if you have any coefficient in front of your variable x, you have to multiply by the reciprocal of that coefficient in order to find the actual antiderivative. So if I just get rid of these 3's and say that that's going to be true with any constant coefficient, your formula is going to look like this. Okay. So I'm going to write all this information on the board just as a summary, but they all work the same way. So at the beginning, let's just start with the one that we just did. If I take the antiderivative of cosine of x, that is going to give you sine of x. Notice here I don't have an a there because I want you to kind of think about these as 2 separate ideas. But the antiderivative of cosine is positive sine because if you take the derivative of sine, you get cosine. if you take the antiderivative of sine of x, this one you have to be a little bit careful with. But the antiderivative of sine of x is going to be negative cosine of x. It's not just cosine of x. If I take the derivative of cosine of x, I get negative sine. Right? So since the derivative of cosine is negative sine, but I want a positive sine, that's why I have to put an extra negative in here. So as you're trying to get used to these, kind of remember that the opposite happens. When I take the derivative of sine, I get cosine. When I take the derivative of cosine, I get negative sine. But working it backwards, if I take the antiderivative of cosine, that's the one where the sign stays the same. But when I take the antiderivative of sine, the sign changes. So I should have said that a little bit differently. When I take the derivative of sine, the sign doesn't change. If I take the derivative of cosine, the sign does change. And vice versa. The antiderivative of cosine is the one where the sign does not change. The antiderivative of sine forces you to change the plus or minus sign there. And then finally, the last one is a little bit weirder, but the antiderivative of secant squared is equal to tangent. And that's still just working backwards. The derivative of tangent is secant squared. And so those are the three big ones to remember. If you want, you can check the textbook for the antiderivatives dealing with expressions with cosecant and cotangent and such. But in general, these are the two main ones. You'll occasionally run into a secant squared, but beyond that, it's not something where we would typically run into the other weird trig functions. Okay, so those are the big ones. And what I would typically tell you then is that if there's a coefficient in front of each one of these x's, all you have to do then is keep the coefficient in front of the x, but then multiply by the reciprocal. Okay, so I'm going to go ahead and rewrite these as formulas, but that's the only thing that's going to be changing. If this is a cosine of a times x, this is the one we saw earlier, then you're still going to be dealing with sine of a times x, but you have to multiply by the reciprocal of that a. If you're looking at sine of a times x, you're still going to get a negative cosine of a times x plus c, but you have to multiply by the reciprocal of a. And finally, the last one is the same basic idea. If you have an ax here, then when you take the antiderivative, you have to have a 1 over a along with your tangent a of x, or sorry, a times x plus c. Okay. So these are a little bit trickier to get used to because you have to keep track of the sign, and because tangent had a weird derivative, it feels like secant squared is going to be a harder thing to work with, but it's not. It's just something to recognize as part of your formula. All right. So let's do one example here, and then we'll get to our last topic in section 4.9. Okay. So let's say that you're asked to take the antiderivative of 2 sine of 5x minus cosine of 3/4 x. Okay. So once again, it's a little bit of keeping track of your formulas, but you're splitting this up into both pieces here. This is just a constant coefficient, so you're multiplying 2 times whatever the antiderivative is. This is where you have to be a little bit careful. The antiderivative of sine is negative cosine, so you're going to get a negative cosine. And notice I just left a space here because there was a coefficient. We're going to have a reciprocal out front, but it's the antiderivative sine is negative cosine of that 5x. And we have to multiply on the outside by the reciprocal of that coefficient. So multiply times the reciprocal of 1/5. Sorry, reciprocal of 5, which is 1/5. And then in the other one, the derivative of cosine is sine. We're taking sine of the exact same expression. But again, we have a coefficient in front of the x, so I have to multiply by the reciprocal of that coefficient. And there's going to be a plus c at the end. And maybe I didn't need to have the parentheses a second go around, but putting it all together, we're going to end up with negative 2/5 times cosine of 5x minus 4/3 times sine of 3/4 x plus c. And so Just a reminder here, don't get going overboard. These are completely separate numbers. Multiplying the whole cosine by 2/5 and taking cosine of 5x are two completely different ideas. So please don't try to multiply these. Likewise, don't multiply those. And that's the antiderivative involving trig functions. All right, so I know that just having one, maybe two examples of each type here, it's not a huge amount of practice, but again, I realize this video has probably already been going for 45 minutes, maybe even longer. So I'll just leave it up to you to send me an email, ask questions if there's anything when you're finding antiderivatives that you're struggling with. The last thing that we're going to talk about, though, is finding a specific antiderivative. Okay, so here, these are called initial value problems, which I don't want to necessarily give a definition for. I'll kind of describe why it's called an initial value problem here in a second. But let's say that we're asked to find the antiderivative of, excuse me, now let's just use a polynomial here. Let's just take the antiderivative of x squared minus 7x plus 2. Sorry, I should say if. So we're finding the, instead of a antiderivative, we're finding the antiderivative of that, such that, and I should have given that a name, but let's say that this is f and this is our capital F, but f of 1 is equal to 3. And so let me just rewrite this. I realized with the way I need to describe things after the fact, I should have put in f of x in front. So find the antiderivative of f of x equals to that expression where the antiderivative evaluated at 1 is 3. Okay, so this is called an initial value problem because, first of all, it's giving you a value that we know about regarding our antiderivative. So it's called the initial value problem because usually the only thing you know about a problem is what's happening at the beginning. So much of our derivatives and antiderivatives are with respect to time and actual applications. If you know that the value of something at the beginning before time starts ticking, that means that value is usually a 0 in applications. But here I wanted to give us something a little bit more, because it was just a polynomial, I want to give you something a little bit different than just a 0 here. So the big picture is if you know something about the antiderivative, you can find a very specific antiderivative. You're not looking for a plus c at the end anymore. You're looking for the specific antiderivative that corresponds with the x squared minus 7x plus 2, where also if you evaluate it at 1, you get 3. Okay. So in these sorts of problems, all you're really doing is kind of two steps. You're finding the antiderivative, and I hope you guys can read this. I'm having to stretch up here. You're going to find the antiderivative and go ahead and use the plus c at the end. And then the second step, once you find that antiderivative, is just plug the information in. Plug in 1 for x, well, not here because we have to plug in the antiderivative, but you plug in 1 for x and set it equal to 3. That's going to allow you to solve and figure out what c is up there. So once we're finding the antiderivative using c, now plug in the given values and solve for c. And I guess I should say maybe rewrite the whole answer, but I think that's clear. I'm not going to write that as a whole extra step here. Okay, so if I'm finding the antiderivative of x squared minus 7x plus 2, this is once again just kind of working step by step. Here, increase the exponent by 1 and multiply by, sorry, I pointed the wrong one, multiply by the reciprocal of that new exponent. And the next term, keep that -7 as a constant coefficient, raise the exponent by 1, so you'll get an x squared, multiply by the reciprocal. Okay. And then finally, this is kind of our constant rule. You can still call it maybe an x to the 0th if you wanted to and raise it by 1 and multiply by the reciprocal, but our constant rule just says put an x next to it. Okay. And then because we're supposed to solve for that plus c initially, go ahead and put that in there. Okay, So that was really step one, other than maybe doing a little bit of simplifying. Step two is plugging in x equals 1 and setting this equal to 3 so that this works out the way it's supposed to. So step two says we're going to take that x and replace it with 1. Let's simplify here just a little bit, right? It's negative 7 halves, but then replace the x with 1. Replace the x with 1. And then finally, we know when we replace the x with 1, this whole thing should be equal to 3. Okay, so the rest of this is just solving. And all those 1s disappear, so you're going to be left with 1/3 minus 7 halves plus 2 plus c is equal to 3. And the rest of this is really just kind of busy work. I'm going to have to hopefully write a little bit, whoa, sorry, my whole camera moved there. Write a little bit lower here, and hopefully you can still see this. But first of all, subtracting 2 from both sides, save a little bit of space, is going to give you a 1 over here. And then from there, it's just a matter of how you like to solve things. You can multiply to get rid of the fractions if you want. I would tend to get a common denominator and just deal with this. So the common denominator is going to be a 6. So multiply by 2 to get a 2/6 here. Multiply by 3 to get a 21/6 here. And for that matter, over here, this is going to be 6/6. And so now we're just putting things together. 2/6 minus 21/6 is negative 19/6 plus c is equal to 6/6. Add that to both sides, and we're going to end up with c is 25/6. Okay. So the final answer here is nothing more than taking this value of c and plugging it into the c that we had in our first step. And so here we've got 1/3 x cubed minus 7 halves x squared plus 2x plus 25/6. And that, once again, is not a family of functions anymore. That is the one specific antiderivative that has the property that when I evaluate at 1, I should get 3. Okay. So there's not a whole lot going on here. It's really just one extra step. Find the antiderivative of whatever it was that you were given, plug in the value, solve for c, and then plug it back in. And I will say that for now, these are almost always polynomials because we don't want to have you have some sort of weird expression that has sines and cosines and exponentials all set equal to a number. That's almost impossible to solve. But we want to make sure that we're used to this because one of the main applications of antiderivatives is dealing with acceleration, velocity, things like that. So what this boils down to is that if we have just a little bit of information about the acceleration and the velocity of an object, we can actually figure out where it's at. Okay, we can figure out its position function. So this is our one example of an application here. Let's say that an object is accelerating at a constant rate of negative 32 feet per second squared. Okay, so just a reminder, it's been a while, but don't worry about the per second squared. That's just the label for acceleration. Don't want to make a huge deal about this, but this is approximately the acceleration that's caused by gravity. So if you just drop something from the top of a building, this is how fast it accelerates until it hits the ground. Okay, so we'll say that an object is accelerating at a constant rate, so it's not changing, the constant rate of negative 32 feet per second. And, excuse me, we know that, after, say, 3 seconds, it was traveling at a velocity of, we'll just say 10 feet per second. and its height, I guess we're using a dropped object since I said it, but its height was, say, 50 feet when it was dropped. Okay, so obviously it was not moving until it was dropped. And so when it was dropped, I thought about making this part of the problem, but when it was dropped, that certainly means that t is equal to 0 there. Okay, so a lot of information here to keep track of, and hopefully we can fit this all on the board. But this is enough information to allow you to find an equation or a function that gives the height of the object after, say, t seconds. And of course, as with all applications with math, we don't know right at the beginning where this relationship is going to be valid, but at some point it's going to hit the ground. So this is going to be a function that gives you the correct information as long as it's still in the air. Of course, once it hits the ground, it's not going to be valid anymore. So we're just going to assume that these t seconds that we're talking about is the position as it's still falling. And so again, a whole lot of information that's given to us in the problem that, I guess a lot of words, but there's really only three pieces of information. We know the constant acceleration. We know what's happening in exactly 3 seconds with its velocity. And we know exactly what's happening at 0 seconds with its actual height. Okay. So the first thing that we have to do is just review what we know from, so I go the other way, from section 3.6, where we know that the position function, which in this case, the position would be the height. So I'll use h for the height. If I take the derivative of the height function, that's going to give me the acceleration function. Okay. And we know that if we take the derivative of the acceleration function, I said that completely wrong. I apologize. I'm not going to start the video over now. You don't get the acceleration when you take the derivative of the position function. You get the velocity function. Okay, so chalk that up to being just be careful here with the information. But if you take the derivative of the height, so the rate of change of the height is the velocity of the object. The rate of change in the velocity is the acceleration. Okay. And so that's the relationship we had from section 3.6. Well, we can take this back then, or work this backwards. This means that if I take the antiderivative of the acceleration, I'm going to get the velocity. And working backwards with the velocity here, if I take the antiderivative of the velocity, it's going to give me the height function. Okay, so again, there's technically a plus c in there, but we're going to be able to find that plus c with the information in the problem. That's why I didn't want to go too far with that. Okay, so our objective here is we are given the acceleration. It's a constant function. It's always negative 32. So we can use the given acceleration function, find this antiderivative to find the velocity. Once I have that antiderivative, I can plug the information I know in about the velocity to figure out what that constant is that we talked about not knowing. That gives us an exact velocity function. Once I have that exact velocity function, I can take its antiderivative to get a basis for the height function, and then plug in the information I know about its height. Okay, so maybe rewriting all of this information so that I have a little bit more space here. We know the acceleration is constant, negative 32 feet per second. So what that is telling us is that the acceleration function, doesn't matter what time we have for t, the acceleration function is a constant, negative 32. Okay, the second line tells us that the velocity is 10 feet per second when t is equal to 3. So we know the velocity here at 3 is 10. And then finally, we know the height function, when we evaluated 0. So again, when t was equal to 0, the height was 50 feet. Okay. So I know there were a lot of words here, but it all boiled down to just knowing this information. And I guess I've already said it, so I'm not going to rewrite it, but now we just need to take antiderivatives and find constants. Okay. So we know that the velocity function at any time t is the antiderivative of the acceleration function. We know the acceleration function is negative 32 for this problem. And then finally, the antiderivative of a constant tells us just to tack on the variable. So this one, we're taking it with respect to t, so we're going to get a negative 32t, but we have that constant, right? So right now, we have that the velocity function is negative 32t plus c. Okay, so from there, we just plug in this information. We know that if I put in 3, so if I put 3 into this equation, we know that we should be getting out 10 feet per second. Okay, so I just labeled this to make sure it's clear where this came from. We don't need this part of it, but we know that this has to be true. This is just quick arithmetic and solving. So add the 96 to both sides and we get c is equal to 106. And so altogether, you're taking this initial information. We know that our velocity function has to be negative 32t plus 106. Okay, so I guess I'm going to have to do some more erasing, so we'll copy this on the board, but we're taking these two pieces of information, which is what we just did, and that tells us the exact velocity function. Velocity is negative 32t plus 106. Okay, so just to reiterate, the first step, you have to have the plus c, and then you take the information that was given to us to figure out what the constant has to be. So that has to be the velocity function for that particular object. Okay, so now that we have the velocity function, we can use the relationship that the height function at any value of t is equal to the antiderivative of the velocity function. We just found the velocity function to be negative 32t plus 106. And the antiderivative here, a little bit more complicated, but not much. But the antiderivative here, the negative 32 is the constant coefficient. The antiderivative t, you raise the exponent by 1, multiplied by the reciprocal. And the 106, as we said before, you just throw in the variable next to the constant coefficient, and then we have the plus c still. Okay. And then just a quick bit of simplifying, half of 32 is 16, so this just becomes negative 16t squared. So putting this together, we know that h of 0 needs to be 50. So I have negative 16 times 0 squared plus 106 times 0 plus c has to be 50. And I don't think this is particularly tricky. This is why in the other example, I chose something other than a 0, but we end up with that disappearing, this disappearing, and we just get the c is equal to 50. Okay, so putting that together with what we had up above here, the height function has to be negative 16t squared plus 106t plus 50. Okay, and that's all the problem asks. It just asks what is the height function, or what is the height after t seconds, and so we're done here. So again, it was just a matter of taking this antiderivative that we came up with, along with this information here, to give us our final function. Right, so if you're working one of the textbook problems or even one of the My Math Lab problems, it'll sometimes ask you to do some things along the way. So in my math lab, maybe it would give you all this information, then ask you to find the velocity after 5 seconds, or then maybe find the height after 3 seconds, or ask you, when is the height 50 feet? All you're doing is this for your antiderivative work and your function work, and then plugging in the appropriate numbers based on the question itself. Right. So again, I know that just one example piece is not all that much, but at the same time, this video has gone on forever. So I'll stop here and again, leave it up to you guys if there's any concerns or questions that you want me to address again. So have a nice day.